Remember to push the record button this time. Okay, so in the last class, as usual, I ran out of time, but we were talking about data transfer, and just kind of to recap a little bit, we know that if I want to store a binary value, a 0 or a 1, I can do that by some kind of way storing a voltage, and we said that the presence of a voltage, we can represent that using the binary digit 1. The absence of a voltage, we represent that using the binary digit 0. The voltage levels are kind of arbitrary, but we choose 5 volts to represent a 1, a 0 volts to represent a 0, and all we got to do is figure out a way to store those voltage levels to represent those binary bits. It turns out it's pretty easy. We can use a device called a capacitor to store the voltage or charge. We can use a device called a flip-flop. There are ways to do that, so that's not a problem at all. But the second question is, once I get those bits stored, once I sample an analog signal, I store it as a digital code. I sample those points and I store those points as a code. What do I do with those digital codes? How do I move them around? And so we talked about kind of 3 scenarios where you have those 0s and 1s located in the microprocessor. You want to move them around in the microprocessor, or maybe outside the microprocessor, but within the digital device, within the computer or PLC. Maybe I want to move the bits from the microprocessor to the memory, or from the memory to the microprocessor. How do I do that? And then the third scenario is, what if I want to move those bits outside of the machine? What if I have a computer on one side of the room and a printer on the other side of the room, and I want to move those bits from the computer to the printer so I can print out a picture, so I can print out a Word document? How do I go about doing that? Or even bigger than that, what if I'm in Cincinnati and I have a family member in California and I want to go www.something.com. I want to get on the internet and send that person the file from my computer to their computer. What you're really sending are these bits. You're sending 1s and 0s over a huge network called the internet. Again, how do I do that? And so we showed you this picture here, and I talked about, to understand how to move bits, you first have to understand what we mean by digital pulse. And I'm not going to go through the details of that again, but you realize from the previous discussion, there's 2 types of digital pulses. There's a positive going pulse, and there's a negative going pulse. And in the last class, what I tried to emphasize is that the positive going pulse is what carries what we call the 1, the high, the binary 1. And the negative going pulse, we can use that to represent a 0, but not just a 1 or a 0. Those pulses are actually moving. They will move down a wire, they move through a radio wave, they move through a fiber optic cable. We can move those digital pulses around, therefore we're really moving bits. So we looked at that, and then the second thing I want to just kind of recap on, I want to, probably one of the most important concepts we talked about in the last class, is that when we have those pulses, we put them together, what we get is something called a waveform, a digital waveform. And there's 2 types of waveforms we can talk about. There's a waveform that repeats itself. We say that the waveform is repeating, it's periodic. And then there's the non-periodic waveform. And so if you're looking at your screen right now, I'm showing you a picture of both of those. If you take a look at this, the very top one, this one, you see how it repeats. You know, it starts right here, this pulse, it goes high, it stays high for a while, it drops off, and then it stops right there, and anything after that is a repeat. So this is a periodic waveform, and what we said about periodic waveforms, all periodic waveforms have 2 characteristics we can talk about. They have what we call period. The period is how much time, how much T-I-M-E, how much time does it take for it to repeat? That's the period. And then the other one is frequency. How often does it repeat? How many cycles? A cycle being one repetition. How many cycles do? And usually we look at the number of cycles in a time space of 1 second. So how many cycles do I see maybe go down the line in a second? And we call a cycle per second a hertz. So the periodic waveform, we actually use it for control. And in most digital devices, in your computers, in your cell phone, and anything that has a microprocessor, they're going to have circuitry in it to generate this periodic waveform. And the term we use for it is clock. The clock is the heart of any and every digital device. It's the heart of any, it makes everything go. So everything happens in the computer, everything happens in your cell phone on the click of a clock. And by click, I mean one of these repeating cycles. So that's important to know. The other type of waveform that I'm showing you, and they have on this diagram waveform A, B, and C. You see how these don't repeat? So these don't really repeat. We use non-periodic waveforms to carry data, to carry ones and zeros, to carry bits. And so periodic waveforms are for control. Non-periodic waveforms, that's the way we move the information around. So the question becomes, and this is kind of where I kind of had to speed up in the last class and ran out of time. I think I was showing you this diagram, and I said, all right, well, if I have a periodic waveform, and I understand that if I have a positive going pulse, let's say I have a really big positive going pulse like this, I know that represents a series of ones, or is it just one huge one, or is it a bunch of ones sent in series? How do I interpret this? And the only way to do it is, and these are the steps, and I'm actually going to give you an exercise today. We'll go through an exercise today. I want you to just do a simple calculation, and this will prep you for the quiz. And I don't know when that quiz I'm going to activate. I feel I'm behind already, of course, and I want to activate that quiz, but I want to give you some time to go through this stuff. So you want to make sure you can do what we're going to do right now, this calculation. And then at the end of this lecture today, we'll go over the objective sheet that I gave you on the first day of class, and that quiz is going to be kind of based on the lecture sheet. But I think I'm going to give the quiz towards I don't know, maybe over the weekend or something, to give you some time to go through your notes. But we'll talk about that at the end of class. So here's what you have to do, and they kind of already done it in this diagram. Notice that we said that we call the time for one repetition. The time, and in this diagram here, the clock, the signal starts here, and then it starts to repeat right there. So the length of time between these two lines, that's what we mean by period. How much time does it take for one click of the clock for one repetition? That's the period. That's the period of any signal, whether this is what you're looking at now on the clock. These are square waves, but you can have, you know, in your other classes, you dealt with a series of sine waves, a series of maybe of triangle waves or sawtooth. This is the same for any periodic signal, that the time for one repetition is called the period. And then I gave you a couple equations to relate period and frequency, and hopefully you wrote that down in the last class. But basically, if you didn't, the period is the reciprocal of the frequency, and the frequency is the reciprocal of the period. So given if I know how fast the clock is clicking, given the period, I can determine the frequency. But typically, when you buy a computer or when you buy a flat panel TV set, they don't give you the period, they give you the frequency. They say that this microprocessor is so many gigahertz. So you have a frequency to work with. You can take that frequency and you can convert that to period. And the important thing to know about period is period defines what we call the bit time, BIT dash time, the bit time. So the first thing to do, if I want to know, in this example that I'm showing you, focus on waveform A. I want to know, okay, how many bits am I sending in this waveform right here? Well, the first thing I got to do is figure out the period. So let's say on the quiz, or it'd be kind of hard to do this through the computer, but what you want to do, and this is called a timing diagram, and this is common to digital circuits. So this example that you're looking at now has a name. It's called a timing diagram if you want to Google or YouTube it. And it just kind of tells you when things happen in a digital device. But what you want to do with a timing diagram is you first start with a clock, the clock signal, and then you drop these perpendicular lines down like they're showing you here, and that represents the period of the clock. because that period of the clock is also the bit time. So what that means is right here on waveform A, that's a single binary 1. And this is a single binary 0. And this is a single binary 1. Here's a 0, and so forth. Down here, you see, look at waveform B. You didn't know, if it wasn't for the bit time, if you didn't define the bit time, you wouldn't know how many ones this positive going pulse represents. But because you've defined the bit time with these dotted lines, you know that you actually have a 1 here, and you have a 1 here. You know that here you have 2 zeros, and you have a 0 here. So if you were going to actually do this from scratch, what I'd have to give you is step 1, and what I would probably do is give you the frequency. You're more likely to be able to determine the frequency of, let's say, your computer than the period. Usually that's given, it's marked. That's not hard to find. So let's say I give you the frequency. The first thing you would do is you would take that frequency, you would use the equation, period is 1 over frequency, and you would use that frequency to find the period. And once you find the period, you would take a ruler, and if these lines weren't already given, you neatly draw these lines down, and they would intersect the waveforms. Now remember, this top waveform right here, the one that says clock, that's called in the computer your control signal. That's control, and everything below it, those non-periodic forms, that's your data. That's your data. So what you do is you draw these perpendicular lines down, these lines down, and that would define your bit time. And then you can actually go in here and you can actually mark the bits that are being carried in these waveforms in figure 1-2. Now let me think about something now. If you look at this, if you think about a graph, and I'm having a hard time drawing with my mouse. So if you think about a graph, let's say I took this waveform right here, waveform A, and I put it on this graph. I wonder if I can change, let me see something. I wonder if I can change the color. I don't know how to change the color. Anyway, I wonder, let's say if this is a graph. So on the horizontal axis here, you have time, and here you have your voltage level. And so let's say you take waveform A, and this is pulse 1, this is pulse 2, this is pulse 3, and so forth. If I move that waveform over to here, now I'm going to not set it on top of the t-axis because you won't be able to see it. I'm going to leave a little bit above it, but I just want to show you something real quick so you can think about this. If that waveform was sitting over here like this, say you had a waveform like this, maybe something like that, right? So this square wave, this one right here, if you think about time on the horizontal axis, t equals 0 is right here at the origin. And then the first tick mark might be here, and then you got the tick marks down here. In other words, time increases as you move that way. So even though students tend to think of, when they see this square wave, they think of like this wave actually moving down a wire that way, and you think that you would see pulse 8 first. Actually, the first thing you would see would be this one. So I don't know if you follow what I'm saying, but the first one on the page that you see here on the clock is this one that I have circled. Let me erase this. So if this were actually moving down the wire, you might think that if it's moving this way, that this right here, pulse 8, would be the first one that you see. But actually, the first pulse is this one. Because if you lay that on an axis where this one is time, this first pulse right here is right here. So in time, this one is first. So when you actually read the bits that are being transferred, you don't really say, all right, this one's first and this one's second. You actually start over here. This one is the first one to be transferred. This is the second to be transferred, and so forth. We'll come back to that in the practice problem I'll give you in just a second. But let me go back because I want to just kind of emphasize, get out of here, what we talked about before. So again, the steps, given this on a homework, quiz, whatever, I have to give you a timing diagram, and I have to give you either the frequency or period, more than likely you'll get the period. You take a period, you use, more than likely I'll give you the frequency. I'm sorry. The frequency is easy to get. Usually it's marked on the device, on the computer, whatever. So given the frequency, you use the formula, period is 1 over frequency, and you can figure out the period, and then you got to know, well, the period, what that really is, it defines the time for 1 bit. We call that the bit time. So then you take your ruler and you just draw these dotted lines down the page that you see here, because now we know that the period of this clock defines 1 bit down here in the data. So right here, I know instead of having a 1 that goes from here to here, in reality, I have 2 1s defined by my bit time. I got a 1 right here, and I got a 1 right here. And from what I just said a second ago, you know the first one to be transmitted or moved is not this one, even though it looks like it. If you think of this waveform moving from left to right, the first one to move in time is this one. This one happens before that one. So you kind of got to think about that. It's not really intuitive, but if you put it on the graph, it makes sense. So you would, given the frequency, you use the frequency to determine the period. The period is the bit time. You take your timing diagram, you draw these lines on it, and once you draw the lines on it, then basically you define your 1s and 0s, you define your bits in here. So you can come in there and put your 1s in there and your 0s in there. If I ask which bit is transferred first, it's always this one over here on the left, because t equals 0 is on this side, and then you'd have your calculation done. So 3 steps: given the frequency, find the period, use the period to define the bit time, and the bit time tells you how many 1s and 0s the data waveforms carry. So pretty simple. We'll do a practice problem today. The other thing we talked about in the last class that's pretty important is, well, once I have I can see how I can use a digital pulse to move these bits back and forth now. But there's actually 2 ways you can do it. And this is kind of, I think we mentioned this in the last class. I'm pretty sure we got to this point. There's what we call serial, we're talking about data transfer. There's what we call serial data transfer and parallel data transfer, and it's just exactly what the words mean. Serial means we're moving these 1s and 0s in single file, bit by bit. And parallel, we're moving them all together in one group. And what you got to remember, what's critical is a bit doesn't move until the clock clicks. Nothing happens in the computer or the cell phone until the clock clicks, when the bit time passes. So on this first diagram, I have and this is actually, I don't know, now they use a USB port, but back in the old days, if you had a computer, on the back of the computer, you had a port called the serial port. I mean, I have old computers at my house that I take apart. Newer computers don't have a serial port, but the old computers had a serial port. And what you would do is you type a letter. Let's say you type a letter in Word, you save it to your hard drive, or you at least print. And what happens is that Word document, which now you know that anything that's digital, whether it's a picture, a document, a video, when you move it around, what you're moving around is 1s and 0s. So when you say, hey, print, then you're going to send those 1s that make up that Word document. You send it bit by bit by bit by bit. A long time ago, and this is way before most of you were born, this is around the beginning of the internet. Not the internet, but the web. There's actually a difference between the World Wide Web and the internet. The internet is the hardware, the structures, the switches, the wires, the routers, all of that. The World Wide Web is software. So I'm talking about the World Wide Web. The internet, that's the product of the late 60s, early 70s, but the World Wide Web came around the 90s, the mid part of the 90s. And in the early part of the web, when you would move data back and forth, you use something called a modem. And a modem is really weird because you had, and I know you guys all have cell phones, but back in the day, you actually had phones that had a wire attached to a wall. You couldn't just walk around with it. And I can actually remember this. What you would do if you wanted to connect up to the web, what you had to do was dial a phone number. I remember something called America Online. And it was a service where, basically a modem service where you would dial a number, you would take the receiver of your phone and set it in the cradle, and all you would hear is a tone. But what you were really hearing is the frequency of those bits being transferred back and forth. And in those days, they transmitted those bits bit by bit by bit in a serial fashion. It was really slow. We'll talk more about that later when I actually can go to a picture. But here's a picture of what I'm trying to describe. In the old days, if you wanted to move ones and zeros from a computer to a printer, there was no need to do it quickly. I mean, printers, most of the time, printers are just sitting there. They spend most of their lives just sitting. So while we can do something on the computer called multitasking. I can type a letter, and once I'm done typing the letter, I can hit print, and I can go off on the computer and do something else, and the computer can do the second thing I'm doing, my second task, but it can also print at the same time. So it was sending those ones and zeros over from the computer to the printer, but it does it bit by bit. So notice in this picture, there's one data line. There's just one line through which those bits can travel. And so if you think about it, from what I said earlier, like this bit right here, that one, even though this is kind of weird to think about, even though you see they have this T7 right there, and this is what I was saying earlier, it looks like this bit will go into the printer first to give me my document. Well, actually in time, if this is T0, this is the first bit right here to be transferred. But that's really not what I'm talking about. What I want you to focus on is notice that there is one line here. There's only one wire through which those bits are transferred. And so each one of those bits are transferred bit by bit in single file, and each bit transfer happens for a click of a clock. So let's say it takes the bit time is 1 second. 1 second. If I had 8 bits I want to move from the computer to the printer, it will take 8 clicks of the clock to move those 8 bits. If my transfer is serial transfer. So you can see this is really slow. Now, you would never move bits that slow. A second is like a century to a computer. So really we talk about, it used to be milliseconds, and now it's microseconds or even picoseconds, the speeds that we move this stuff back and forth now. But the point I'm making is that this process of serial data transfer is pretty slow. Well, what's the other way we can do it? Well, the other way we can do it is the bottom picture. I have, now it's a little hard to see this, but I have over here a microprocessor on the left, and I have memory. And so maybe I'm working on some bits in the microprocessor, and when I'm done, the microprocessor wants to move the bits from the microprocessor over the memory so we can store it. Well, notice in this diagram, they have 8 lines. There's 8 data lines here. And what happens is the same, if you look, I got the same series of ones and zeros as I do on the top. But instead of sending them bit by bit, when that clock clicks, since I have 8 lines, I send a bit across each line during that first click of the clock. Basically, I'm sending all 8 bits at one time. So this is going to be 8 times faster than the serial way of moving these bits back and forth. So the 2 basic types of transfer, when I want to move bits between a microprocessor and memory, or between a computer and some other external device, I can do it serially or I can do it in parallel. And I think I mentioned before, there's advantages and disadvantages to both ways. If from the picture, you can clearly see serial data transport, I only need 1 wire, so it's really simple. So it's going to be inexpensive and simple. That's the advantage. The disadvantage is it's extremely slow. And then the other way, the parallel data transfer is more complicated because I need more wires, but it's a lot faster. So there's a trade-off. Typically, when we have devices like a computer that they don't really need the data real fast, it's better to use serial data transport, and just kind of in general. And then if I need things to move around real fast, like if that microprocessor is talking to the memory, it doesn't have time to wait milliseconds, not even microseconds. It's got to have it right now. So you're going to find that inside the actual devices, you're going to have what we call data buses and control buses, and they're going to move things in parallel. So I said a lot, but what I want you guys to do is I don't know if you printed this stuff out or if you, well, first let me pause. Does anybody have a question about the document in front of you? The computer, serial transport, transfer, parallel transfer, or this timing diagram? Anybody have any comments? Because I want to give you a practice problem once I address your comments. Anybody have any comments, questions about this diagram? Okay, well, what I want you to do is to blow this up. Hopefully you printed this out. I should have in the last class. I should have had you print this out. If you were, face to face, I would have printed this out for you. So take a second, read this. If you got it printed out, then you're in good shape. I've already gave you the control signal. I gave you the clock. And I've already drawn the lines here for you. And here, instead of 3 data signals, there's just one data signal in figure 1-14. And so problem A says it wants you to determine the total time required to transfer the 8 bits contained in the serial waveform. So I'm telling you that waveform A, right now we're going to think that we're transferring these bit by bit down one line. So transferring the serial waveform A in figure 114, and then we're going to indicate the sequence of bits. The leftmost bit is the first to be transferred. And we already said that because we know, t equals 0 is on the left, not the right. So they gave you the frequency of the clock, which is common. And they want you to determine the sequence of bits, and they want you to determine how long will it take to move these bits from one point to another if I do it using serial transfer. So I'm going to pause for a couple minutes. You guys work through that. I gave you the steps. Step 1, you got the frequency. Take the frequency, change it to the period. Period defines the bit time. Draw your lines. I've already done that for you. And now you know the bits. You know the bits, whether they're ones or zeros, and then you can just count the number of bits you have and how many ticks of the clock that you have, and you know the period, so you can figure out the exact time to transfer the bits. So I'll be quiet for a minute. You guys go ahead and work through it, and then we'll look at the solution together, see if you're thinking about it the right way. Give you about maybe 3 minutes. Okay, you guys keep working. but it gave you the frequency here. So the first thing you're going to do is you're going to use that frequency to get the period. So we said the period is 1 over the frequency. So you'll use this formula. Now the unit for frequency is the hertz. You've seen that in megahertz, gigahertz, kilohertz. But a hertz is equivalent to an inverse second. So the unit is a 1 over second. So when you actually do the math here, you get the proper units. You get your period in seconds. And you probably want to convert that to usually milliseconds or microseconds or picoseconds or something. So that's your first step. And then once you do that, if you didn't have these lines here, you go ahead and you draw these lines down, because that defines your bit time now. Now you know that this is 2 bits right here. Okay, so that's your first step. And then once you draw your lines down, you can actually mark your bits in here. That's a 1, a 0. And then you can just count, well, how many clicks of the clock do I have? That's the period. How many periods do I have? And basically, this is a click. This is another click. That's the second. That's the third. That's the fourth, fifth, sixth, seventh. Looks like there's 8 clicks here. So whatever your bit time is, if you take your bit time and multiply that times the number of clicks of the clock, or how many bits you're transferring, that'll give you the total time of transfer. So that's kind of what you're doing. And this is only if you're doing it serially. So those are the steps you should have done. And if we move over here to the sheet here, I worked it out for you, and you blow up that. So you can kind of see the steps I'm talking about. So the very first thing is to determine your period. What we've done here, so we use that frequency to get the period. That period, 10 microseconds is the width of that waveform, that clock waveform. So that's the bit time. So it takes, in this data, 10 milliseconds of that non-periodic data waveform, 10 milliseconds of it defines a 0 or 1. So once you break it down, what you have is this is actually 2 1s. There's a 1 there, a 1 there, 0, 1, and so forth. So once you see that, you now know that each click of the clock is 10 microseconds. Well, how many bits do we have to send? We got to send 8 bits across that wire, and each bit takes 10 microseconds. So the total time of transfer would be 80 microseconds. Now, I know you're sitting there thinking, well, damn, that's fast, 80 microseconds. No, it isn't. My microsecond to a computer is like a year. A microsecond is a long time. I mean, it used to be fast, but devices are ultra fast now. So a microsecond, the microsecond, a computer can do a billion things. So even though it seems like a short time, that's actually pretty slow by today's standards. So now notice it says, all right, what's the sequence of bits? Well, it tells you here the leftmost bit, the one, even though it looks like this 0, the waveform is moving that way. So if you were standing here, here's you, and you're looking at this, you think you see this bit right here go by first? In reality, in time, this is the first one. T equals 0 is over here. That's the first tick. That's the first one that will go by. This is the first bit that's transferred. That's the second bit that's transferred, third, and so forth. So, don't fall for the trap thinking, well, this wave is moving from left to right, so this is the first bit that's transferred. You got to think about where it exists in time, T-I-M-E. So that would be the first part of this practice problem. And then the second part, he says, all right, well, it's going to take a total of 80 microseconds to move it if I transfer this data serially. What about if I do it in parallel? That's part B. Well, if I do it in parallel, instead of having one line, what you'll have is you'll have 8 lines. You'll have your device, wherever this thing is coming from, and you'll have 8 lines. You'll have 8 of these lines. And this bit right here, like that 1, it's sitting right here. It's sitting over here on this device. The 1 is sitting here, and the 0 sitting here, and the 1 and the 1 that's sitting there. And when that clicks, they all move over here at one time. So basically, if I have parallel data transfer, it only takes one click of the clock to move all of those bits. So it only takes 10 microseconds instead of the 80 that I have here. But notice my circuitry for this is going to be way, way more complicated, which means it's going to be way, way more expensive. So again, there's a trade-off. So one of the objectives, one of the things you got to be able to do is calculate the time data transfer for data transfer serially and for data transfer in a parallel fashion. And the other thing is the order of the bits in time, T-I-M-E. You want to know how to order or sequence the bits. So I don't think I have this up on your canvas, but I can put it up there if you need it. But it's pretty. These are pretty simple calculations. Anybody have any questions or comments on the calculations?
My one question is, would you not have 9 like bits because it has to end somewhere?
Usually, that actually is a really good question. So usually when this is a little bit more complicated than what I'm showing here. Usually when you're actually doing this, and it really depends on the network, but let's say you're going to move bits. Right now I'm moving bits from my camera to your computer. So yeah, you're right. You got to have a start bit. Actually, you have a start bit and an end bit, and they move these bits. I don't want to go too much into this, but when you're moving these bits across the network, they move them in what we call packets. And you can think of a packet as just a group of bits. They scoop up a group of bits, and that packet has information in it. One piece or two pieces of information it has in it. You're right. It has a bit that says when this packet starts, and it has a bit that says when the packet ends. And depending on how we're moving these bits, the packet could have other information in it too. Like one thing it could have in it is, what if I'm sending some kind of information from me to you through a network in forms of zeros and ones? How do I know how do I know the bits that you received is actually what I sent? And so that you can go to, it can get kind of complicated. So the short answer to your question is yes. When you're moving these bits inside of a real device, there's other information I'm not showing here. You can have bits that signal when the information starts, when it stops, information that checks it's called error checking to see if what the receiver got is what I sent. It gets a lot more complicated. I think the point here is just to have kind of a basic understanding of what's going on in the digital device. And then when we move over to the PLCs, I think you'll appreciate what we're doing right now, because you really don't need to know this to actually program a PLC, but it really does help to understand what's kind of going on under the hood. So we talk about in your book, they call it an image table, and PLCs, they call it a data table. You'll know exactly what you're looking at. So yeah, there's a little bit more to the story than this, but this is just kind of the bare bones facts of the way to think about this. So yeah, you're right. Good point. Anybody else? Okay, I wanna shift because I'm running out of time, and I use the word shift. That's kind of a pun because I actually want to talk about shifting bits. Remember we said there was 3 scenarios. There's a scenario where I might want to. I got a microprocessor and I got some memory, right? So memory basically is temporary storage for zeros and ones. So there's memory and there's storage. So memory is where I store bits temporarily, and storage is where I store it long term. So example of that is if you're using Microsoft Word and you're looking at it on your screen, your Word document exists in memory. If you were to unplug your computer and if you didn't save your Word document, it's going to go away because memory requires power to hold those zeros and ones. If you don't want your Word document to go away, then what you would do is you hit save occasionally, but when you save it, you're now saving those zeros and ones to the hard drive or to some other drive, and that's what I mean by storage. So memory is just kind of a scratch pad, a temporary holding place. And so if I want to move those bits from the microprocessor to memory, I usually do that using what we call parallel data transfer. And then the scenario where you're moving it like from a device that doesn't care about speed, maybe from my computer to a printer, you can use serial if you want, but they have other ways of doing it now. But what I really want to focus on now, I want to go inside the microprocessor, because what does it mean to process something? Micro, you know, that means small, but the word processor, why is it called a microprocessor? What does it mean to process something? And so basically what you do, the essence of the word process means you take data and you turn it into information. Processing, I mean, strictly speaking, means taking data and turning it into information. And why do you do that? Well, that's kind of philosophical. Some kind of way you give the data meaning. But what I want you to think about, and this is actually pretty amazing, inside of the device itself, the microprocessor is the computer. Inside that microprocessor, all you're really doing is shifting bits back and forth. You're just shifting it back around. Now, this is not a class on embedded systems or microprocessors, but I do want you to know a little bit about what's going on inside of this device. And when you actually go inside the microprocessor, there's a device called a register, like a cash register, but it's called a shift register. So inside of the actual microprocessor, what I want you to do is just think of, well, you guys are familiar with Excel, the spreadsheet program. You have that grid system in Excel. So think of a grid like that, but instead of a grid, each cell is like a little box that you can put a 1 or a 0 in. Like, just think about one row of an Excel spreadsheet. Matter of fact, let me show you this picture. I think I have, look at this picture right here. So the way to read this picture, if you zoom in on it, now I told you to think about one row of a spreadsheet. So you got this one row like this. Now a shift register is an actual thing. And what I mean by that is we're going to talk about things in this class. Some of the things I talk about, they're what we call virtual devices. They don't really exist. They only exist in I guess you call it the metaverse, or I don't know, virtual. They're virtual devices. But then there's the real things that you can touch and feel. So, and I don't have to distinguish between the two, but a register is, if there used to be a store called Radio Shack where you can go and buy electrical parts. I think now you can either do it online, or there's a place called Micro Center. You can buy like Arduinos and the resistors and stuff. But if you had an electrical store you can go to, you can actually go to the electrical store and say, Mr. Salesman, Mrs. Salesman, I want to buy a shift register. And they'll say, okay, what size register do you want? And the size determines the number of bits that register can hold. So all a register is a device designed to hold zeros and ones, but you got to load it up some kind of way. So this diagram right here shows a 4-bit shift register. And the way to think about it is this device has these cells in it, and each cell stores a 0 or 1. Now I know over here in this picture they're showing 1, 2, 3, 4, 5 of these, but really what this is showing is it's showing you how you load the shift register. So the way to think about it is this very first row right here. This row, well, here I have it over here. So initially it says initially the register contains invalid data or zeros. Now let me talk about that. When you have a digital device, you cannot not have something in the device. Let me say that a second time. If you have a digital device, it's impossible to have for something not to be inside of it. You got to have, if you have a register, you got to have something in it, and what's in it is either going to be a 0 or 1. If you put it there, it's called data or information. If it was there when you started, you don't know what it is, we call it garbage. Okay, so the point is you got to start with something. So in this particular example, we assume that the shift register has all zeros in it. Now I color coded these for a reason, because what we want to do here is we want to take, we got 4 bits over here, and I want to move these bits over into the register. Okay, so what happens is, now the thing to remember when you're reading that timing diagram I talked about earlier, and when you're moving bits, nothing happens until the clock clicks. When you have that bit time. That's one thing, no matter what happens in your cell phone, it happens on the click of a clock. And so if I have 4 bits, and you can see I'm going to move these in bit by bit. So this is serial. I'm moving these in the serial way. It's going to take 4 clicks of the clock to completely load this register. But look how we do it. Initially, the first click of the clock, this one right here, moves over into this space right here. So here it is. That 1 is moved over here. And then this 0 right here is shifted over here 1 place to the right. And on the next click of the clock, I got this 0. Well, that 0 is loaded in. So here's the 0. So this 1 is moved over 1 place. The 0, which was here, has now moved over to here. And you can just kind of follow this, that if I want to completely load this register, it's going to take 4 clicks of the clock to completely load it if it's wired in a way to where I'm putting in bit by bit. And then I have a register that's completely loaded. So now I've loaded this register right here. Now that's another way to store zeros and ones, and it's something called a register. The technical name for these little cells is called a flip-flop, but you don't really have to know that. But just a shift register. This is what happens inside of the microprocessor. Those zeros and ones are stored in devices called registers. Now that's important if you're wondering what the heck does this have to do with PLCs? Well, in the PLC, when you connect up your hardware, like your switches or your whatever you're going to control, you're going to connect it up to something called a module, input or output module. And each one of those, and I'll show you pictures of this, you'll know what I'm talking about. But each one of those modules basically is going to ultimately represent a bit in the PLC. And so we want to talk about how those bits are stored and how they're moved. And I'll show you an example of that. And because of this lecture we're having right now, when we get to that point, it's going to make a heck of a lot more sense. But all I want you to focus on now, I got like 5 minutes, but all I want you to do is focus on is how these bits are moved. Look at this at the bottom. These are the type of shift registers you can have. So on the quiz or exam, expect a calculation like we did, where I give you the bit time or the frequency, and I ask you to determine the time for serial transfer, the time for parallel, the sequence of the bit, like we just got through doing. But another thing I might ask is about when you're inside the actual microprocessor, moving data in and out of these registers. How do you name the process? I'm going to the camera for a second. Let me get off of this and go to the camera. So it's actually really, really, oh, don't forget to email, text me if you did. Send me a text, 494-6162. You know the story. Put your first and last name in it. But let me show you 2 things before you leave, guys. I want to show you something real quick. I'm already behind. I don't know how I'm going to get caught up, but anyway. So what I just showed you is here's your shift register. And they have 4 cells. You have 1 line in and 1 line out. So if I had some bits over here that I want to move in, I move them in bit by bit by bit. This is called serial in, serial out. And this is the slowest way to move bits inside of a digital device. Serial in, serial out. I don't have to do it this way though. Maybe instead of having 1 line in and 1 line out, maybe I have 1 line in and then I have 4 lines out like this. So to get the 1s and 0s into the register, it's going to, since I have 1 line, it's going to take 4 clicks of the clock. Whatever the bit time is, 4 times that bit time. But eventually I'll load this like this. And those bits are there. But when I want to get it out of the register, I have access, since I have 4 lines here, I have access to each of those bits. It's only going to take 1 click of the clock to get these to drop down to here. So this is serial in, parallel out. And then, of course, I can have it the other way where, well, why don't I just do this? If I have a register, I can have lines out like this, and I can have 4 lines in like this, and maybe my bits are sitting right here. Well, here, let's just use these. So I got a 1, a 0, a 1, and a 1 sitting there. And in one click of the clock, all of these drop down into here. So I got parallel in, and then one click of the clock, I can read them. So I have parallel in, parallel out. So you should be able to, just from the picture, name this. Okay, there's so much I want to say, but I'm running out of time, and I want to show you one more document. Real fast, when you read a bit, I mentioned the term read. Reading and writing is 2 different things. Let's say I want to write to this cell right here. I want to put a 0 there. If I write to that cell, then whatever's in there is destroyed, and then whatever I want to put in there is stored. But if I want to read it, when I read that, say I read it and move that 0 somewhere else, the original 0 is still there. So we say that writes are destructive, reads are non-destructive. So I'll say that, but let me show you one thing. I know I'm out of time, but give me just 1 minute. I just want to go over real quick this. I want you guys to look at this, and next class, I think I covered everything on here, but I did some of this real fast because your next quiz is going to be kind of based on this document. And then when you have your first exam, it's going to be, a lot of it's going to be based on this document. So look at this, and in the beginning of next class on Friday, I'll ask you if you have any questions. I think I've covered everything here. This is the objectives for week 1. And the only thing I think I probably didn't talk about is, it's not even on here. Oh, okay, gates. So you don't really have to worry about too much about this. I'll mention that in the next class. But look at this for next class. If you have questions, ask me about it. And if you do, I'll answer it. If not, we're going to move on. We're behind the week already, but we'll move on to the next module, which is available on Canvas now. Module 2, week 2 is available. Homework 2 is available. So get in there and look at that. Look up this objective sheet. If you have any questions, let me know on Friday. And sorry, guys, I went over. Anybody have any questions or comments before I sign off? Okay, great. Then, guys, you have a great rest of the day. It's a lot of material, so I feel like I'm moving too fast. I can only see Jacob's face because he's the only one that has the testicular fortitude to turn his camera on, so I can only see his face. So I don't know how you guys are getting this, but if you have questions, let me know, and then at some point we'll be face to face. And I think the class will go a little bit better when we're in front of everybody. So have a great rest of the day. If you need me for anything, send me a text. Other than that, I'll see you guys on Friday, and we'll pick up, and we'll some kind of way we'll get caught up. See you later, guys.
Have a good one.
Thank you.
Thank you. Have a good one.
Bye-bye.